USGS Landslide Seminar, which is hosted by our Landslide Hazards program and coordinated by Matt Thomas, Jamie Kostelnik, and Steven Slatter. None of them were available to host today, so you're stuck with me, Ben Miras. I think they have this well-oiled machine going, so please bear with me if there are any errors or mistakes. One note is we're under a tornado and severe thunderstorm watch here in Golden at the moment, so if everything crashes, that's what's happening. For those of you who are new to this meeting, you will have the ability to submit questions in the chat window or using the raise your hand feature when turning on your microphone afterwards. But we'll wait to keep questions until the end of the talk and have a managed discussion then. So in the meantime, please keep your microphones muted and your cameras turned off to preserve bandwidth. Just a quick announcement. Next week, we'll be hearing from Dan Coe of the Washington Geological Survey with a talk entitled Communicating Landslide Risk, Landslide Information and Hazards with Maps and Graphics at the Washington Geological Survey. Today, I'm taking on the dual role of hosting and introducing today's speaker, Jacob Woodard, who is a Mendenhall Fellow with us here at the USGS in Golden. Before coming to us, Jacob pursued his bachelor's degree in geology at BYU and earned both a master's and PhD from the University of Wisconsin-Madison, with an emphasis in geophysics and surface processes. His research there was focused on understanding subglacial erosion processes, and I took him to some of my favorite places in the world, like Alberta and Iceland. But promptly after defending his dissertation, Jacob moved with his family here in the summer of 2020, right in the middle of those pandemic lockdowns and the birth of this seminar. And so it was an interesting time and challenging for us to get research going, but Jacob's really excelled and has done some exciting work on landslide susceptibility with new data and new modeling techniques. And so that's what he's going to present to us today. And it's my pleasure to hand the screen off to Jacob. Jacob, thank you.
All right, thanks, Ben. Appreciate it. Yeah, it's a pleasure to be here, and I'm excited to share with everybody some work that I've been doing here at the USGS, basically figuring out ways to make meaningful susceptibility maps over large regions with imperfect data. Here's the government disclaimers that are mandatory. For this talk, first going to go through kind of the problems that we're confronting, and then we're going to try to answer these two big questions that I keep on running into as I'm trying to develop these susceptibility maps over large regions. First is how to manage regions with limited or no landslide data. And to evaluate this, we're gonna investigate the influence of the training domain, or the data that you use to develop your models, and the limits of that data. And the next question that we keep on confronting is how to manage the imprecise data that we have available to us for creating these susceptibility maps. This isn't a unique problem. Basically, any data set that we have available to us is imperfect and imprecise in its very nature. And so how can we mitigate the imprecision with the model output, or how to best represent the model? And to do that, we're gonna dive into different mapping units and the pros and cons of the mapping units and how they can adjust or play a role in displaying the imprecise nature of the input data. So first, introduction. I don't think this needs to be said to this group here, but landslides cause damages and losses of life every year in the United States and across the world. So here's an example of the 1985 landslide that resulted in over 100 fatalities. And then more currently, Hurricane Maria in Puerto Rico. And so this causes damages to life, to infrastructure, to residences. And we can expect that with the changing climate, the severity of these storms that cause these types of landslides is going to increase. Here's an example of a damage to the road. And this causes both damages to loss of life, which is incalculable, but also when you damage the infrastructure, there's a lot of economic losses associated with that. If you have a pivotal road that's closed down for a long time, it's important to try to reduce these losses as best we can. And that's kind of been the objective of my project here. And kind of the first measure that you can do to try to mitigate these losses is with the creation of a susceptibility map. So here's an example of a susceptibility map from Puerto Rico. And as I said before, this is kind of the first line of defense. And so what precisely is a susceptibility map? Well, what it does is that it measures the likelihood of landslide occurrence at a given location, given the local terrain conditions, and that's it. right? It's just a spatial component and typically the outputs are the probability of observing a mapped landslide within a given mapping unit. And so a susceptibility map and a susceptibility model are inherently imprecise. And this is because of the data that we have available for creating these. If we had timing and magnitude, we wouldn't try to create a susceptibility map. We try to create a hazard map, which, as the name implies, incorporates magnitude, time, and location. But over most of the United States and the world, we don't have the timing and magnitude of most of the landslides that we have any sort of information on. And so what good is really a susceptibility map if the output's so imprecise? Well, what it does is that it highlights areas that are more prone to landsliding by using evidences of past landslides. And again, just kind of emphasizing this point, we're limited to this susceptibility output because we don't have the data available for something better. But people have been making susceptibility maps for a long time, and there's a few common approaches that people use for creating these susceptibility maps. First one is a physically based model, and these are, as the name implies, they're able to model the actual physical mechanisms that lead to slope failure. The next one is the data-driven or statistical models, and these include methods like machine learning, fuzzy logic, deep learning, AI, those types of methods where really the output is dictated by the input data. And we'll dig more into exactly how these work because this is going to be kind of the focus of this talk, are these data-driven statistical models. Next are heuristic models, and what these are that a user would basically define what dictates susceptibility. So you can imagine somebody could say, okay, we're going to say that susceptibility is going to increase with slope. And so you could just measure the slope of the terrain and voila, you have a susceptibility map. That would be an example of heuristic model. And then you can also do geomorphic mapping using GIS and field observations to create a susceptibility map. But as I said before, we're going to be focusing here on data-driven statistical models. And the reason for that is because generally over large areas, once again, we don't have the data available for a physically based model. But thanks to remote sensing, that's really kind of gained traction over the last few years. We do have a lot of data that can be used with data-driven statistical models. So how do these models work? The basic idea is you imagine that you have some domain of interest shown here in these figures, and you have some known distribution of landslides shown here by the white dots. And then you can measure the attributes of those landslides. Here on the left, we have slope plotted, and on the right, we have elevation. And so you can gather the slope and elevation of all these different landslide points. And then you can collect data across the domain that doesn't have evidence of landsliding and collect the slope and elevation of all those non-landslide locations. So you have these two arrays of data, landslide data, non-landslide data. You feed that into a model, and that model is designed to differentiate as best it can the landslide data from the non-landslide data. And so hopefully it's obvious here the importance of data, right? This is going to be kind of a common theme or point I'm going to keep on driving home here. Data reigns supreme with these statistical methods. And so with that, we're running into these two major obstacles. How do we deal if we want to create a susceptibility map where we might not have very much data or no landslide data? How can we create a susceptibility map there? And then how to manage the imprecise nature of the landslide data that's available to us to create these susceptibility maps. To illustrate this point, we're going to zoom in to the Four Corners region of the United States. Here I have an image from the national inventory that the USGS has been compiling, and the colors here correlate with the level of confidence and the extent and nature of the landslide data that we have. Lighter colors being low confidence, higher or darker colors being higher confidence. So we're going to zoom in here to Colorado, New Mexico, Arizona, and Utah. And you can see that there's a lot of heterogeneity here, both in the extent of the mapped landslides and in the quality of the landslides. And so you see here in Utah, you have these Colorado landslides that starkly stop at the municipal boundary, which is odd. And then you have varying degrees of confidence in this. And so how do we manage this? The way we're going to manage these regions with no landslide data is that we're going to assess the limits of the training data. And I'll highlight these experiments in the coming slides, but that's going to be the first half of this talk. The next one is how to manage imprecise landslide data. And by imprecise, I'm going to define this here. We mean heterogeneous formats. So for instance, here at the Four Corners region, New Mexico predominantly uses points. The other areas often use a combination of points and polygons. And so how do we manage those? Inaccurate landslide locations, as we've already talked about. The colors here correlate with the level of confidence in the extent and location of these landslides. So how do we deal with that heterogeneity? There's no timing component on basically any of these landslides that are available to us. These are all mapped using predominantly geomorphic mapping tools and GIS. And the level of completeness, we can see that there's relative differences in the level of completeness and what does a complete map really look like? These are all kind of inherent imprecisions that we need to deal with and take account for when we're creating a susceptibility map. And one way that we can kind of accommodate this imprecision is by the choice of mapping unit. And I'll dive into how that plays a role for the second half of this talk. So once again, we're first going to tackle how to manage regions with limited or no landslide data, and then we'll talk about how to manage imprecision in the data. And so to evaluate how to apply a model to areas with poor data, or limited or no data, we're going to evaluate previous approaches that have been done for mapping susceptibility over areas with poor data. And having reviewed the literature quite a bit, I can kind of broke them down into these three main approaches. The first one is applying a model trained on data-rich regions to data-poor regions. And the way we're going to evaluate this approach is that we have 4 different data sets from across the United States, and we're going to train a model on 3 of those 4 and apply that model and see how it performs on that one region that's left out. And this is basically to mimic what most people do with this approach. We're going to do this for each of the 4 areas so we can get kind of a range of the relative performance of this method. The second approach that I've seen commonly used is that they restrict model training and application to regions with shared environmental attributes. And so we selected these regions based off of, one, the quality of the landslide data that's available, but also on the relative similarity of environmental attributes on the continental scale. So 2 of them share a physiographic province, and 1 of them is outside of that physiographic province, but shares a similar ecoregion, and then 1 region is completely outside of those environmental conditions. And so we'll train a model on 1 location that should have high environmental similarity and test it on the other locations to see if constraining by these environmental attributes helps improve model performance. So we're going to do that with these varying degrees of environmental similarity. The last approach is training and applying a model on very sparse but a uniform inventory. And so what I mean by this is that you have some landslide data across the entire area where you want to model susceptibility, but it could be very sparse. And often the way people do this is that they'll kind of scour GIS and just find some locations that they know don't have a mapped landslide or do have evidence of landsliding, but they're not worried about getting a complete repository. And to mimic this, what we're going to do, we're going to use these same 4 regions, but only sample 5% of the available data, develop a model with that 5%, and then test that model on the 95% we didn't use to develop the model. And we'll repeat this several times so we can get distributions. And so now we kind of understand the theory of how we're going to approach this problem. Here are the actual data sets that we're looking at here. So we have 3 locations in Appalachia. We have McGuffin County, Kentucky, Doddridge County, West Virginia, which both share the same physiographic province and level 2 ecoregion. The ecoregions are shown by the colors. The physiographic provinces are shown by outlines. And then we also have Macon County, which is in a different physiographic province, but within the same level 2 ecoregion. And then we also have the Elkhorn Ridge Wilderness in California. And so these are the data sets. And once again, we chose these areas due to the variation in environmental similarity and the high quality landslide data that's available here. And we know it's because of the high resolution LiDAR and imagery that they used, including field reconnaissance for developing these catalogs that we're going to use. All right. So the models that we're going to use, the statistical models that we're going to use is logistic regression. And we're going to evaluate these models using two primary techniques. The first, commonly used receiver operator characteristics, area under the curve, kind of the go-to metric for assessing landslide susceptibility or how well the models. But something that's often lacking when we evaluate susceptibility models is actually understanding what leads to that level of accuracy as reflected in the receiver operator characteristics. And we're going to dive into understanding this relative accuracy by comparing the logistic coefficients within the models. And we'll get more into what that means in the coming slides. It should be noted here that we're not using just the basic frequentist logistic regression model. We're using a Bayesian approach. And the reason is that a Bayesian approach is able to incorporate uncertainty into the estimated distribution of the model parameters. In this case, we're interested in distribution of beta. And a logistic regression model is shown here. We have a linear function that's within a logistic function. And that's basically, and then it outputs the log odds of there being a landslide at a given location. And the basis of the Bayesian approach for logistic regression is what's referred to as Bayes' law. And what Bayes' law is, it says that the posterior distribution of some parameter of interest, in this case, it's the beta, given your input data is proportional to prior probability times the likelihood function. The prior probability is an assumed distribution of beta before you even look at the data. And the likelihood function is assumed to be a Bernoulli distribution of the logistic function as shown here. So for our instances, we're going to use very vague priors. So that way the data is really what dominates these posterior distributions. And so this gives us a distribution of these coefficients, and that allows us to do more statistical tinkering, as we'll show you, than you can generally do with a frequentist approach. So for pre-processing the data, there was a lot that I'm not going to go into, but we followed kind of the standard procedures that people have had success with in the past. We ended up evaluating 64 different predictors, and by predictors I mean aspects of the terrain like slope or elevation. And after we did our pre-processing and a correlation analysis, we reduced that number down to 11. And so that's the model approach. How are we evaluating these? So if you're not familiar with receiver operator characteristics, area under the curve, the basic idea is that it's a measure of how well your model is able to distinguish no landslides from landslides. So if you have a model that's able to perfectly distinguish no landslides shown here in blue from landslides shown here in orange, you would get an area under the curve value of 1 being perfect differentiation. In contrast, if your model does a very poor job of differentiating them, such as this example down here, where it basically randomly chooses, it's equivalent to randomly choosing between landslides and no landslides, you would get an area under the curve value of 0.5. So equivalent to randomly guessing. So you want area under the curve values of near 1, ideally, closer to 1, further from 0.5. And once again, the second way we're going to evaluate these models to understand these area under the curve values are by assessing the coefficients of these models. But because of some inherent properties within logistic regression, we actually can't directly compare coefficients between the different models that we've trained. And so we have to convert these into something called average marginal effects. But all these it's a way of assessing the effect of the variable or predictor of interest within the given model. So an example of this is shown here. These different colors correlate with a different model or different training data that was used to develop that model. And we have our predictor slope, and we have these predictor effects or average marginal effects on the x-axis. And what you can see is that there's variation in the sign and the magnitude of these predictor effects. And so if we take, for instance, Macon County, you can see it has a negative AME value. And what that tells you is that as you increase slope at that area, the model is going to cause susceptibility to actually go down. So that's what the negative sign means. In contrast to all the other locations or all the other models, as you increase slope, you get an increase in susceptibility or in probability, which the model outputs. But The magnitude of that probability increase is variable depending on the magnitude of this average marginal effect. So how is this useful to us for understanding a model accuracy? Imagine that we develop a model only using slope, and we only have Macon County data, and we're going to train our model on Macon County, and we end up with this negative predictor effect, negative average marginal effect value. And then we try to apply that model to any of these other data sets. You're going to get a horrible fit for these areas where you apply that model, because it's going to actually do the opposite of what it should be for assessing susceptibility in those locations. So in this way, these average marginal effects can give us information as to whether or not these different models are compatible with each other, or better said, the location where these models were trained are compatible with one another. And so using these two tools, average marginal effects and area under the curve, we're going to assess these three different methods. So first is applying models from data-rich regions to data-poor, and then also we're going to look at restricting by environmental attributes. And so the next plot, I'm going to show you the area under the curve distributions for these different experiments. So there's a lot going on here. We're going to break this figure down. All right, so first up here at the top, we have what we're referring to as resubstitution. That is, the training data is then evaluated on itself. And so this, you would expect to get relatively high area under the curve values, and we do indeed get area in the curves around 0.7. Lowest value is about 0.65, but relatively high values compared to the other examples I'm going to show you. Down here is where we evaluate the first method that we're interested in, a training model on data-rich areas and then applying to a data-poor area. And these are models that were trained on all the data except for a given location. So all the data except for the MacGuffin location. And then we test that model on that one area that was left out, in this case, the MacGuffins. And you can see here that we get quite a bit lower area under the curve values. So this suggests that maybe this isn't the best approach. Okay, how about constricting or restricting based off of environmental attributes? That's shown up here. And so here's the two data sets that have shared ecoregion and physiographic provinces. And once again, the highest area in the curve we're getting is about 0.6, but we're also getting another example of that's below 0.5, so very poor model performance. Shared ecoregion and different physiographic province, once again, we're getting very low area in the curve values. And really, these restricting by these environments are no better than when you have different ecoregion and physiographic provinces, and those distributions are shown down here. And so it appears that neither of these approaches, training on data rich, applying to data poor, or restricting by environmental similarities, are effective in this case. And so why? What's going on here with this data and with these models that cause them not to be transferable between these locations? Average marginal effects are going to give us this information. So here, hopefully the slope segment is familiar to you. And once again, if we want a model to perform well in a different location, you would expect these to have similar average marginal effect distributions. And across the parameter or the predictors that we included in these models, here's a subset of those. You can see that there's no consistency in sign generally, and definitely no consistency in the magnitude of these average marginal effects. And if we look at the rest of the predictors included in the model, it's the same story. And so because you don't have any consistency in these average marginal effects, a model trained in one location isn't going to perform well in the other locations. And so the poor area under the curve values that we're getting are due to these divergent predictor effects as manifest by the average marginal effects. And so how about this last method, training and applying models on very sparse but uniform inventory? And so again, here, we're only sampling 5% of the data, developing a model with that 5% and applying it to the rest of the data. And here's the distribution of those area under the curve values we're getting. For reference, when we use all the available data, 100% of the available data, we're getting area under the curve values of 0.65. But when we only use 5%, on average, we get an area of the curve value of 0.63. So the drop is not that significant here. So why is this method of only using 5% of the available data effective? Average marginal effects are going to give us this information. So here this might look intimidating, but we'll walk through this. So these different colored lines, as I mentioned before, we sampled 5% about 100 times. And these are those posterior distributions for each of those iterations. The black line here is showing the average of all those iterations, and in red is showing the average marginal effect distribution for a model when we used 100% of the data. And so if we expect the model to perform well, we would expect these average marginal effect distributions to be well aligned with this red curve. And generally across all the predictors that we included in our models, that's what we see. We see consistency here between these red curves and the multicolored lines. And so there's consistency in the predictor effects, even though we're only using a very small subset of the data, 5%, it is still able to capture the influence of the landslide data appropriately to better assess the susceptibility across the domain of interest. And so just kind of drive home this point, on the right, we can see similarity in the AME distributions for slope. And when you train a model on each given location individually, you get quite a bit of dispersion here. And so to wrap up this first section, the unique geospatial attributes of landslides. So you can't really leave an area out and then expect that model to perform well in that area you left out. Limiting by the environment doesn't seem to improve anything. So you can't expect to use level 2 ecoregions and then say, we're going to develop a model on this area where we have really good data and apply it everywhere else because we assume landslide similarities. We've shown that that's not effective, at least over the domains that we analyzed. But using a sparse, uniform landslide inventory is relatively effective. So even if you only have a little bit of data that you can collect across your entire domain, that's better than trying to get a very detailed landslide inventory on a very small subset of your domain of interest. Okay, so we've looked at how to manage areas with limited or no landslide data. Now we're going to go into how to manage the imprecision of landslide data that's inherent with these susceptibility maps. And once again, we're going to dive into the choice of mapping unit. And by mapping unit, generally there's two major mapping units that people use. The first and most common method is the raster-based approach, where you can characterize susceptibility for each pixel or grid unit of your raster with an output that looks something like up here on the upper left. In contrast, another method that's been gaining more traction is the slope unit based approach. And what a slope unit is that it's a way of delineating your domain of interest according to drainage and divide lines. So here we have a watershed from Oregon. You can see that each of these lines correlates with a drainage and or divide line or divide line. And so you can then analyze susceptibility over the whole area of interest. And this gives us quite a bit of advantage when we're facing imprecise input data. So what are these advantages? Well, first, because we're dealing with areas, we're able to apply more statistics to that area of interest. Instead of just taking the mean slope value of each pixel, which is basically what you're limited to with the grid-based approach, because you're dealing with an area with an array of slope values, you can then measure the standard deviation of slope or the max, the min, whatever metric that you think is most appropriate for assessing susceptibility over your area of interest. Alternatively, it's a better way of accommodating the imprecise nature of your input data. And once again, by imprecise, I mean heterogeneous formats, inaccurate locations, or no timing component, and incomplete landslide data. And so this is going to be a little bit theoretical here, but I hope that it kind of drives home the point. So we have imprecise input data. Just the very nature of the data that we have across the US for creating susceptibility maps is imprecise. You feed it into a model, you want the outputs to reflect that imprecision. But by using very high resolution rasters, you're actually showing a precise output that doesn't really match the input data. So a metaphor that I thought of is that it's kind of like putting a go-kart engine in a pickup truck. right? There's an incompatibility there. And if you try to use this pickup truck to go and tow a boat or whatever, it's not going to work very well. It's just going to crash and burn. That's kind of equivalent to trying to get super detailed, very precise outputs of these susceptibility models when the input data really is kind of limited because it's imprecise by nature. To further kind of dive into explicitly how slope units account for these first 2 points, I'm going to show a couple of examples. So the first one is how to deal with heterogeneous formats and then inaccurate landslide locations. For the grid-based approaches, the most common way of dealing with this variation of formats is to convert the polygons into points. So therefore, they're compatible with the other points. And again, this is really applicable for large regions that we're talking about through this whole talk. So you can imagine that by converting these whole polygons into a representative point, you're losing a lot of information that would be available to us if we were able to use the whole polygon. But that's really not tractable when you're dealing with large domains. Contrast, the slope unit approach converts everything to areas rather than points. That is, any landslide point or landslide polygon that intersects a slope unit area would then be mapped as containing a landslide, and then you can develop your model based off that. As far as landslide accuracy, at least as far as the position goes, Jacobs et al. Back in 2020 tackled this problem where they compared grid-based approaches to slope unit approaches, and they measured how resilient these methods were for imprecise locations of the landslides. And they did this by, they had polygons for all the landslides, and then they then buffered those polygons by some amount and randomly sampled a point within that buffered polygon. And so that's basically replicating what it'd be like if you had slightly imprecise or inaccurate landslide data. And that's in contrast to these two other methods where you sampled within the polygon, landslide polygon. And what they found was that they got a larger drop in model performance. So here we have the area under the curve metric using the pixel-based approaches compared to the slope unit approaches, where here on the right, you can see that the drop in model performance is less drastic. And so if slope units have all these advantages, hopefully I've illustrated the advantages to you and you're a little bit convinced that these might be something worth entertaining. Why don't more people use these? Well, after I was convinced that slope units are the way forward, at least for the size of domains we're interested in and the data we have available to us, I ran into the problem of the current methods for delineating these are either very laborious, you can manually delineate these things, very slow, and or if you use an automatic method, most of them are, the size of these slope units are arbitrarily set. There are examples of those that are not arbitrary, and they do parameter sweeps that are very, very slow for optimizing the scale of these slope units. And so there isn't really anything out there that is fast and effective at delineating slope units. And so we wrote an algorithm that I'm calling SUMak, or slope unit maker, and it overcomes these challenges of the past approaches. First, it's very fast. It's able to, it automatically runs in parallel. You can throw it on a cluster, and it's parameter free. There isn't anything that a user needs to dictate within this algorithm, and it automatically adjusts the scale of the slope units according to the local terrain morphology. And I'll get into more explicitly how that works in the coming slides. There's minimal pre-processing. Really, you give it a DEM, an area of interest, and it'll spit out the slope units. And it's all open source, programmed in Grass and R and Tau DEM. And so a user could adapt it to their needs. Okay, so how does this algorithm work? It uses something referred to as a constant drop law. Constant drop law is, it says that as you go up Strahler stream orders, which is shown here in this figure on the left, if you have a fluvial dominated system where the system, the morphology is controlled by fluvial processes, you expect that as you go across these Strahler stream orders, you would get a consistent drop in elevation between these stream orders. Once you get to the stream order that you get a statistical difference in the drop in elevation, it's been showed by Tarbot and others that you're no longer in fluvial dominated system, but rather a hill slope dominated system. And so what we do is that we go through different thresholds for flow accumulation, and then we find that where this constant drop law breaks. And right at that point, we delineate these watersheds. So that's basically the largest watershed that captures hill slope processes. And then we split these watersheds by their longest flow paths. And so this outputs what would be recognized in the field as a slope. Just to compare our method to the other method that's commonly used, it's a great algorithm developed by Alveoli, and it's called R.slope units. And this kind of really laid the foundation, really allowed slope units to gain traction, but it's very slow. So we delineated the island of Sicily, which is an area that was already delineated using R.slope units. And we wanted to compare how our algorithm compared to theirs. And you can see the relative outputs. Tau DEM here should be SUMak. And so ours are shown in red, theirs is shown in blue. And so there isn't a perfect match between the two. But if you look at the whole island and quantify a metric that they use to optimize, R.slope units uses to optimize their model, which is this V, it's an area normalized local variance. And what that basically is, it's a measure of the homogeneity of aspect within each slope unit, which is argued to be a good slope unit should have pretty uniform aspect. And these are the distributions that we get. So using SUMak and using R.slope units, there's quite a bit of overlap between these two distributions, suggesting that while theirs is a little bit better for as far as this metric is concerned, ours is remarkably faster. In fact, across the country of Italy, it would take our algorithm about 3 days to process the same area that took R.slope units 3 months to delineate. And they had 4 times the number of cores and 5 times the memory that we had. I delineated this just on my local laptop. And so really SUMak is an effective means of delineating large areas for slope units, and you get very good results. And so now I just want to kind of illustrate the uses of slope units and kind of bring it back to how it's able to deal with imprecise data. Again, putting the go-kart motor in a pickup truck. We're going to kind of try to illustrate that point here. And we're going to do this with 3 different locations. So 2 locations from Western Oregon. We have the Umpqua watershed, there we go, watershed, and then the Kalapuya watershed in Western Oregon. And then also we're going to use the island of Puerto Rico. For the Puerto Rico data set, we actually used an event-based landslide catalog from the 2017 Hurricane Maria. And we'll dig into how slope units are effective for event-based susceptibility maps also. So as I said, we're going to compare slope unit outputs to grid-based outputs. And because we're dealing with variable formats in these data sets, both points and polygons, we need to use some sort of standardization procedure. And we use the most common, an array of different methods. So first, for using a 10-meter DEM, we take the highest elevation point within each polygon and convert that into a point. We also take the middle value of each polygon and convert that to a representative point. And then we take the highest point also using a 30-meter DEM just to show, make a slightly more conservative map using larger mapping units. And then also we're going to take multiple points from each polygon using a 200-meter spacing, again with a 10-meter DEM. And just to see if any of these can approach the model performance of the slope unit-based approaches. For our models that we're going to compare, we're going to use a frequentist logistic regression and XGBoost. We use 2 different models just so we can see that we're getting consistent results between the 2. And as far as predictors, the predictor data, we're going to keep it very simple. We're only using elevation, slope, aspect, and curvature as far as the static variables. And for the Puerto Rico data set, because it is an event-based catalog, we're also going to include kind of a trigger parameter that's soil moisture using the SMAP data, which is shown by people that have looked more closely at Puerto Rico as being an effective measure for susceptibility for Hurricane Maria. For the 2 slope unit maps, we're going to develop models using only the median values, predictor values within each slope unit, and then also another model using the median and standard deviation values. Model evaluation, we're going to use area under the curve. We're also going to throw in an additional metric, which is called the Breyer score, which is just the mean square error between the observation and our model outputs. And so we want lower values there. And so let's look at the outputs. Let's look at the results here. Up here at the top, we have the two raster-based approaches, and I'm showing the best performing results here from the raster-based approaches. And on the bottom, we have the slope unit outputs, and these are outputs using the median and standard deviation of each slope unit. And so a few observations here is that generally they both highlight, similar locations of having both low and high susceptibility values. But the raster-based approaches are able to show a lot more variability in these probabilities across these domains. And while this level of detail can be advantageous, the high resolution rasters may be requiring too much detail from the models trained with imprecise input data. And this can lead to poor confidence in the model outputs. So again, these maps were created with data with heterogeneous formats, points and polygons, somewhat inaccurate probably locations. There's no timing with any of these landslides, and there's no real measure of the level of completeness. And once again, I don't even really know what that means, but yeah, there's no way of really measuring how complete an inventory is. In contrast, the slope unit-based approach, because it uses a larger mapping unit, it is more conservative. And in my opinion, it's able to better accommodate kind of the imprecise nature of this input data. Again, the lawnmower or the go-kart engine inside of the pickup truck. That's what we're trying to not have here. So just to kind of further compare the Umpqua watershed, here's the distribution of known landslides over this domain. And you can see that the landslide deposits here cover almost the whole area. And so in my opinion, what you would expect a useful susceptibility map to do, at least over the scales we're interested in here with our input data, is to model most of this area as being highly susceptible. And looking at the Calapooya data sets, we see a similar thing. Again, here's the distribution of landslides. Here are the two model outputs. If we want a more quantitative measure of this effect, we've here plotted the percent area against the probability. And so if we look at the Umpqua data, the two slope unit-based approaches are shown here in green and yellow. You can see that it gets much higher proportion of the area at higher probabilities, in contrast to the grid-based approaches where really the highest proportion is around 0.5. So it's more nebulous in that sense. And at the Calapooya, it's less stark, but you can also see kind of a similar thing where both the highs and lows are more extreme with the slope unit-based approaches as opposed to the raster. All right, let's look at the event-based catalog from Puerto Rico. So here's the distribution of landslides from Hurricane Maria. And at the top, we have the raster-based approach using a 30-meter DEM. And then down at the bottom, we have the slope unit-based approach. And I think we're seeing the same things here, right? Looking at the percent area, once again, it's less stark here than it was for the Umpqua watershed, but you do still get higher proportion with the slope unit based as opposed to the raster base. Looking at the model metrics, area under the curve. So here we have all the different grid-based approaches that we use. So that is the different standardization procedures we did to get the polygons and points consistent. And in bold here, we have the slope unit based maps, and we're looking at logistic regression in red and XGBoost in blue. And so hopefully you can see that generally across each of the domains that we studied, you get a higher area under the curve, which suggests better model fit when you have when you use slope units in contrast to grid-based maps. Brier score is another metric, again, mean square error, so we want low error values. And you can see that in bold, we have lower Brier scores generally with the slope unit-based approaches in contrast to the raster-based approaches for both XGBoost and logistic regression. All right, so wrapping up this section. Hopefully I've convinced you that slope units are a powerful alternative when you're dealing with the scales that we're dealing with, very large regions. And again, this might not be as applicable when you're trying to analyze the susceptibility over a smaller area and you might have more detailed data. But the scales we're looking at here, large areas, it is a very powerful alternative. It's able to provide an effective solution for inconsistent and imprecise landslide data. And it increases the model accuracy as shown by the two metrics before. And the conservative output better matches the input data. So you're keeping the go-kart a go-kart. You're not trying to put your go-kart engine in the truck. All right, let's wrap things up. So in conclusion, developing a meaningful landslide susceptibility map over large regions is a very difficult problem. We've investigated here where susceptibility models can be applied. And we found that, at least over the study sites that we looked at, every region needs to have some sort of representation in your training model for it to be applicable over the entire domain of interest. So using one concentrated landslide data set and then applying it to other areas with assumed similarities to where you trained your model probably isn't a very safe approach when you're dealing with large scales. Slope units are an effective mapping unit for imprecise data that's commonly available for creating these susceptibility maps. And I've shown how SUMak is a new, fast method of implementing slope units to hopefully allow slope units to gain more traction and for more people to take advantages of these benefits that slope units provide. So with that, I'd be happy to take any questions. You can read, the paper just got published on the first half of this talk in JGR Surface, and hopefully the SUMak algorithm manuscript will be out in not too long as well. So yeah, I'd be happy to take any questions.